Hi everyone, welcome to Differential Calculus. Today we explore lesson 2.6, limit at infinity. Number one, limit at infinity. Let's take a look at two examples. In the first example, given the graph below, find the limit as x approach infinity of fx. From the graph, as x approach infinity, the output approach 1. So the limit here is 1. And notice that 1 is the horizontal asymptote. Horizontal asymptote, y equal 1. Limit x approach negative infinity of fx. From the graph, right, we see the output is approaching negative 1. Meaning that limit x approach negative infinity of fx is negative 1. And also notice that the horizontal asymptote is y equal negative 1. Evaluate limit x approach infinity 1 over x is another example. So to do this, we can use the table. X 1 over x. Let x get bigger. So begin from 10. 1 over 10, 0.1. 100, 0.01. 1,000, 0.001. It looks like as x get bigger, approaching infinity, the limit is 0. And so from here, the limit is 0. I also want to point out that even though infinity is not a real number, any real number divided by infinity, it's going to be 0. So that is just for you to quickly figure the limit. A real number divided by infinity is 0. Okay, it's a pretty cool note. Let's move on to a few more examples. We're gonna figure out the following limit. In the first example A, limit x approach infinity, 2x squared minus 1 over x squared plus 1. Notice that the limit here depends on the leading terms in the numerator and in the denominator. So this is the same as limit x go to infinity, 2x squared over x squared. Yeah, we only use the leading terms. You can simplify this. Limit x go to infinity, 2. And therefore, it's just 2. Wow, pretty cool. Example B, limit x go to infinity, root x squared plus 1 minus x. Well, this is not a rational expression. And if we do the direct sub, we're going to get infinity minus infinity, which doesn't mean anything because infinity is not a real number. We can multiply by the conjugate. Root x squared plus 1 plus x over root x squared plus 1 plus x. And see what we can get. Limit x go to infinity, x squared plus 1 minus x squared over root x squared plus 1 plus x. Yay! And we have a limit x go to infinity. 1 over root x squared plus 1 plus x. From here, we can do a direct sub, as you can see from the note. It's 1 over infinity, which is 0. Wow. One more example. See, limit x go to negative infinity. Root 9x squared minus 1 over x plus 1. Well, this is not a rational function. And one thing is the limit is going to negative infinity. So as x go to negative infinity, x is a negative number, so it will be negative root x square. Okay. And so 1 over negative root x square is the same as 1 over x. Okay. What I'm going to do here is that I'm going to multiply by this quotient. Multiply by 1 over negative root x squared over 1 over x. So they're the same. We just multiply by the number 1. And then from here, limit x go to negative infinity. We have negative root of 9x squared minus 1 over x squared. Down here is x over x plus 1 over x, or x plus 1 over x. And from here, simplify before taking the limit. Negative root of 9 minus 1 over x squared over 1 plus 1 over x. So if we do a direct sub, then we see that negative root 9 minus 1 over infinity is 0. 1 plus 1 over infinity is 0. And therefore, it's going to be root 9 over 1 with a negative in front minus 3. Yay! Pretty cool. As you can see, when we used limit as x go to infinity or negative infinity, what we have, the number, they are the horizontal asymptote. So let's move on to horizontal and vertical asymptote. Definition: the line y equal L is called a horizontal asymptote HA of the curve fx if either limit x go to infinity fx equal L or limit x go to negative infinity fx equal L. Another definition: the line x equal A is called a vertical asymptote VA of the curve fx if at least one of the following is true. Well, the limit x approach A on the left or on the right side has to be either infinity or negative infinity. Example, find all vertical asymptote and horizontal asymptote of fx. A, fx equal x minus 3 over 3x squared minus ax minus 3. Let's factor and simplify. 1 times x minus 3 over x minus 3, 3x plus 1. Well, we can cancel out the x minus 3. And this tells us that we'll have a whole at x equal 3. Some people call it a removable discontinuity. 1 over 3x plus 1. Meaning that the function is undefined when the denominator is 0. Or x equal negative 1 over 3. Yeah, because there is not a whole, it's gonna be a vertical asymptote. Okay, so we got the first vertical asymptote. Next, for horizontal asymptote, we just have to figure out limit x go to infinity, fx, and limit x go to negative infinity, fx. Okay. Limit x go to infinity is limit x go to infinity of 1 over 3x plus 1. And then from here we can do a direct sub. 1 over infinity is 0. Similarly, limit x go to negative infinity, 1 over 3x plus 1. With the direct sub, we also get 1 over negative infinity. Well, that is also 0. And this tells us that y equal to 0 is a horizontal asymptote. Let's confirm the answer with decimals. We're going to graph it using decimals to confirm. Okay. Ta-da! I'm going to graph the original function x minus 3 over 3x square minus ax minus 3. As you can see, we will have a vertical asymptote right there. And we also have a horizontal asymptote. Pretty cool. Let's get back to the example and do another one. Here comes the second example. Root of x squared plus 1 over 2x minus 1. Well, we cannot factor and simplify. We know that gx is undefined when 2x minus 1 equal to 0. X equal to 1 over 2. Ta-da! This number is the vertical asymptote. For horizontal asymptote, we're going to have to figure out the limit x approach infinity, gx, and limit x approach negative infinity, gx, because sometimes we have more than one horizontal asymptote. Limit x go to infinity, root x squared plus 1 over 2x minus 1. Now we're going to use a trick of multiply by the number 1. And in this case, notice that as x go to infinity, x equal to root x squared. So we can multiply the top by 1 over root x squared and the bottom by 1 over x. quotient is the same. That's the number 1. Using algebra, then we can simplify this to be root of x squared plus 1 over x squared over 2x minus 1 over x. And this is the limit x approach infinity of root of 1 plus 1 of x squared over 2 minus 1 of x. We do the direct sub, and that will give us root 1 over 2, which is 1 over 2. Yeah, what this number tells us is y equal 1 over 2 is a horizontal asymptote. So now let's take a look at limit x approach negative infinity of gx. Limit x go to negative infinity. Root x squared plus 1 over 2x minus 1. And for this one, it's a little bit different though. Because as x go to negative infinity, x has to be the same as negative root x squared because it is a negative number. So we're going to multiply by 1 over negative root x squared instead. And that was 1 over x. Yay, multiply by the number 1. And then from here, we see that get pretty similar result. X approach infinity, negative root x squared plus 1 over x squared divided by 2x minus 1 over x. So for this one, similar. Work out the similar step, and we have negative of 1 over 2. What this tells us is y equal negative 1 over 2 is another horizontal asymptote. Let's do a Desmos graph here to confirm the answer. New graph. Root x squared plus 1 over 2x minus 1. Ta-da! Yay! 2 horizontal asymptote and 1 vertical asymptote. Pretty awesome. Thank you for watching. I hope you found the content useful. I'll see you in the next video.